Okay, good afternoon everyone. I'm Martina Caruso and today I'm presenting the main outcomes of my PhD research work, which was mainly focused on the development of a life cycle framework for the integrated assessment and retrofitting of buildings. I will start with an introduction on the current climate change and global warming emergencies. I will continue with a description of the proposed framework, ending with the description of two case study buildings applications. So let's start. In recent years, several targets and objectives have been set towards the sustainable development of our planet. In 1997, indeed, the Kyoto Protocol represented the first international agreement which committed all state parties to significantly reduce greenhouse gas emissions. So we started dealing with climate change issues more than 25 years ago. In 2015, the Paris Agreement represented another international commitment with a view to mitigate the impact of climate change by keeping the rise of global average temperature below plus 1.5 degrees Celsius above pre-industrial levels by 2100. Such a major objective is expected to be achieved through two minor targets, major targets. The first one is the so-called Objective 1, which is a 55% reduction of greenhouse gas emissions compared to those in 1990, which is expected for 2030. And the second one is carbon neutrality by 2050. During 2015, also the 2030 agenda was set, which is an action program setting 17 sustainable development goals, including the 11th one, which is strictly related to the sustainability of cities and communities. So the one the nearest to our profession. In the Conference of Parties number 26, which was a climate change conference which was held in Glasgow last year, was kind of a first checkpoint of this very ambitious process of decarbonization. After this conference, the main question was, are we really on track towards these objectives? This plot shows the projections of annual global greenhouse gas emissions expected by 2100. What we see are 5 different scenarios. The first one is referred to as policies and actions, and it will be our future scenario if we only consider current policies and already implemented actions. So if we don't do more than what we are doing now, we will get an increase of global average temperature between 2.5 and 2.9 degrees Celsius. Which, if we recall that our objective is 1.5, we are completely off track. The second scenario is 2030 targets only, and it consists in the implementation of 2030 objectives only. The third one is referred to as pledges and targets, because it not only considers 2030 targets, but also long-term strategies, including, for example, carbon removal from the atmosphere. The fourth is instead the most optimistic scenario we have, which considers not only all the policies just mentioned, but also all the announced ones. So what we immediately see is that those 4 scenarios are completely different from the 1.5 consistent one. And another important number is the 2030 emission gap, which is the difference which is expected from the annual global emissions expected in 2030 in the most optimistic scenario if compared to the quantity that we need to be consistent with the 1.5 scenario. And we see they are more than 25 gigatons of carbon dioxide. So what are the main consequences of climate change and global warming now? So what happens if we fail to reach our goals? When I say ours, I really mean ours, in the sense that all of us is involved, including earthquake engineers. So some of the main consequences of climate change are already visible today. We know, for example, extreme weather events. Maybe most of you recall the hurricane that happened in Catania last year. Then we observed already rising sea levels, melting glaciers, desertification and land degradation that in the future surely will cause climate migration, as well as loss of wildlife and biodiversity and the development of climate-sensitive diseases and pandemics, as well as food and water scarcity. Maybe now you will be wondering why I spent all this time talking about climate change and global warming. I hope that this time serves the purpose to really highlight and understand that we all need to make our contribution against this possible future. And we as building engineers should be aware that the construction sector is responsible for the 50% of raw material extractions, the 36% of total energy consumption, the 37% of global carbon emissions, and at least 1/3 of the total waste production worldwide. The typical strategies that are used to increase building sustainability are: first, reducing the energy demands of buildings; second, change the power supply by using zero energy technologies; third, addressing embodied carbon in construction materials. So the typical association is building sustainability, building energy efficiency. However, we need to change our way to talk about sustainability, because today it should be broadened to other concepts, including seismic safety, for example. Indeed, if we just look at the European building stock, the 80% of buildings was built before 1990, which is the year when modern seismic design requirements were mostly introduced in building codes, and the 40% of buildings is located in highly seismic region. So, what if we have a building where we make an energy efficiency upgrade and then an earthquake occurs? We will have a building where we lost the investment for the energy efficiency upgrade, and we have a building where that we need to repair or even reconstruct if it collapsed. So, do we think that this kind of building is really sustainable? Hence, the 65% of buildings in Europe would need an integrated intervention of retrofitting, which should consider both seismic and energy aspects. To do so, to the purpose, we need to change our approach to design and retrofitting of buildings. The standard approach typically starts with building performance assessment. And what happens is usually that the structural engineer performs structural and seismic analysis, whilst at the same time the energy practitioners performs energy performance assessment in a sectoral manner. Then they continue independently with the preliminary design process of retrofitting solutions, the final design process, the production of construction materials, up to building management. But we need to really make a change in our approach to design and retrofitting of buildings and embrace a life cycle thinking approach, as was introduced and further discussed by Passoni et al., which really include additional steps in the standard approach to building retrofitting, where sustainability is explicitly considered. Indeed, if we look at the plot, we have a pre-screening phase before the preliminary design of retrofitting constructions, where we which acts kind of a filtering of available retrofitting solutions. So we will disregard all unsustainable retrofitting solutions and take into account only the sustainable ones. The other step is the decision-making process that may be helpful in the identification of optimal retrofitting solutions after the preliminary design and before the final design, which may be based on relevant criteria, including environmental impacts, for example. And lastly, the classification and rating step. So finally, I'm at the main focus of my PhD thesis. What I did during those years was to develop a decision-making tool for the identification of optimal retrofitting solution, and I'm proposing a new classification scheme for buildings. So let's start from the decision-making tool. First of all, I just wanted to do an overview of building life cycle, which starts with construction, then it continues with the operational phase, during which the building has its own seismic and energy performances. The seismic performance, as we all know, can be assessed by the use of average annual losses due to potential seismic events, whilst the energy performance can be assessed through the use of the quantity of primary energy consumption, or the costs, or even the related carbon emissions. Then, of course, we can have a retrofitting option in our building that would change the seismic and energy performances of our building. Finally, we have the end-of-life phase of the building that, unfortunately, today mostly consists in demolition. Since we are dealing only with retrofitting, however, from now on, I'm only considering from the post-retrofit building life cycle. When I talk about integrated assessment and retrofitting, this means that I want to deal with seismic and energy issues in a combined manner. So we need some common parameters to assess the integrated performance of our building. And such parameters may be in terms of economic, environmental, and social impacts. Now I will go through all of them step by step, and I will highlight the parameters that for me were relevant in a decision-making process. Let's start from the first parameter, which is an economic one, and is defined as a life cycle performance metric in monetary terms. It is calculated considering the contributions of the retrofitting intervention, the average annual loss, and the energy consumption, both evaluated through the post-retrofit life, and the cost of demolition of retrofitting materials, all normalized by the building floor area and the expected post-retrofit life of the building. The second parameter is the payback period, which represents the number of years that are expected before achieving the break-even of the retrofitting investment. The third parameter is an environmental one and is defined as the life cycle performance metric introduced before, but in terms of quantity of equivalent carbon emissions. The last one is a social parameter, because I felt it was relevant to include in the framework the calculation of expected losses due to seismic hazard. So the fourth parameter is the number of casualties that can be computed with the preferred casualty model. The one I'm showing here is the FEMA P58 one. So once we have the four parameters, I thought it was useful to use radar plots to visually determine the optimal retrofitting solution. Radar plots look like the one I'm showing here, where each axis corresponds to a specific parameter. So if we have more than 4 parameters, this shape will look differently. So here we will have life cycle costs, emissions, payback period, and average annual loss of life. I assumed that life cycle costs, emissions, and average annual loss of life for all retrofitted configurations were normalized by the corresponding values in the as-built configuration, whilst the payback period would be normalized by the extended post-retrofit life of the building. That's why you see in red the line corresponding to 1. Every configuration above 1 will be worse than the as-built configuration. Let's make an example to better understand how it works. Here we consider a building in its as-built configuration where costs, emissions, and average annual losses are equal to 1 for the definition of normalization, and the payback period is 0 because we have no investment for retrofitting. Assuming we have 3 different retrofitting options, we can identify the optimal retrofitting solution as the one that corresponds to the smallest resulting area. In this case, the integrated intervention, which concurrently minimizes all 4 parameters. The second tool I'm proposing is an integrated classification scheme for buildings, which is based on 2 parameters, which are life cycle costs and carbon emissions, as they were defined in the previous slides, and which is of course inspired by the already existing seismic risk and energy classification, and where carbon emissions are explicitly considered. Using the same example of before, we can have a situation where the seismic strengthening or the energy efficiency upgrade would produce a significant reduction of only 1 out of the 2 parameters. So we will not get a class upgrade, and we only move horizontally or vertically. Instead, if we consider an integrated intervention, we may have an integrated reduction of both parameters, which may lead to a class upgrade, of course, in this case, 2 classes. Now I will move to the description of 2 case study buildings applications. The first one is a school building located in Abruzzo in central Italy, and the second one is a residential building in Liguria, northern Italy. The reasons for choosing 2 buildings were, first of all, the need to demonstrate the practicality and the applicability of the framework, and secondly, to observe how the outcomes would change with buildings with different characteristics and different destination uses. The first thing we need to do is the integrated assessment of the building in its as-built configuration. So I needed to perform earthquake loss assessment and energy performance analysis. Starting from the earthquake loss assessment, it was carried out through the well-known FEMA P58 approach, whose main steps are the hazard analysis, the structural analysis, the damage assessment, and the consequent loss assessment, which can be carried out in terms of economic losses, environmental impacts, and casualties. Here we have the results for the 2 buildings. We notice here that 2 different analysis approaches were used for the 2 buildings. Indeed, for the school building, a pushover-based loss analysis was carried out, and only direct costs due to seismic hazard were considered. Instead, for the residential building, no linear time history analysis were carried out because one of the retrofitting options was seismic isolation, as we will see later on. And in this case, I also considered indirect costs due to building inactivity during repair activities, because in residential building, occupants' relocation is much more important, while in a school, repair activities are typically carried out during holidays. Moving to the energy performance assessment, here we have the results. Also in this case, I used 2 different analysis approaches to be coherent with the seismic counterpart. For the school building, indeed, I used a semi-stationary analysis, and I only considered the contribution of energy consumption for heating. Instead, for the residential building, I used a dynamic analysis, and I also included the contribution of cooling, hot water, and elevator, which are more relevant in a residential building rather than a school. What you see here is that the school building appears to be much more impactful rather than the residential building. If we just look at the environmental impacts, we see an 8% of the total replacement impact. In addition, for the school building in particular, those estimates are even higher than the seismic counterpart. And the reasons, again, are mostly two. The first one deals with the characteristics of the building envelope, and the second may be related to the type of simplified and thus more conservative analysis. Once known the major building deficiencies, I could move to the design of some 8 retrofitting options for each building, including seismic strengthening only, energy efficiency upgrade, and integrated interventions. Starting from seismic strengthening, I considered for the school building external joint strengthening and the introduction of new reinforced concrete shear walls. For the residential building instead, I only considered the introduction of a seismic isolation system at the top of ground floor, coupled with cross steel braces. Concerning instead energy efficiency upgrade, I considered 2 possibilities for the school building of vertical thermal insulation. The first one composed of expanded polystyrene panels, and the second one consisting in the application of a very thin ceramic insulation layer. For the residential building, I thought about the substitution of windows with more energy efficient ones, thermal insulation of wall air gap with cellulose fibers, roof insulation, the introduction of a photovoltaic system, and finally a global energy efficiency intervention that couples all the interventions above. Finally, for integrated interventions, I considered for the school building joint strengthening coupled with beams and columns halting, external joint strengthening coupled with a vertical insulation of the envelope, and reinforced concrete walls coupled with either EPS panels or the thin ceramic insulation layer. For the residential building, I chose seismic isolation plus photovoltaic system, and lastly, seismic isolation coupled with the global energy efficiency intervention. So finally, we get the results. I'm only showing 4 out of the 8 retrofitting options just for the sake of space. And what we see here is that the optimal solutions for the school building was the one coupling reinforced concrete walls and the thermal insulation with EPS panels. For the residential building, instead, the optimal solution was seismic isolation plus photovoltaic system. What we can see here that the last 2 plots for the residential building are quite similar, and one could argue that the previous intervention led to reduced carbon emissions. However, this option is much way invasive rather than the other one. So this is just to underline the importance of the role of the decision maker. The results of the school building were also superimposed on the proposed classification scheme, where we can see that options like strengthening of joints over here is even worse than the as-built configuration, because maybe this option is too costly or too impactful for this specific building, whilst the optimal solution led to a class upgrade instead. The last thing I tried to do was to vary site locations of those buildings to see how the results would change based on the climatic and seismic conditions at the site. For the school building, which is located in a region with average climatic and seismic conditions, I selected other two sites. The first one with warm weather and a high level of seismic hazard, and the second one with a cold weather and a low level of seismic hazard. Interestingly, the optimal solution is always the same for all the three sites, and it is an integrated solution. The reason may be related to the specific characteristics and efficiencies of the school building. For the residential building instead, which is located in a warm site characterized by an average level of seismic hazard, the other two sites were selected considering the same level of seismic hazard at the time of construction only. So they are another site with average climatic conditions and a low level of seismic hazard. And the optimal solution is roof insulation only, indeed. Lastly, for a cold site with a high level of seismic hazard, the optimal solution, as expected, is a global seismic and energy integrated intervention. Let's make some conclusions. I believe I demonstrated that the framework provides a viable and a practical approach for a life cycle-based classification of buildings and for the identification of optimal retrofitting solutions. But the geographic site is important has a role in the estimation of economic, environmental and social impacts through the building life cycle, that both seismic and energy performances are relevant in life cycle evaluations, and that integrated interventions are most of the time convenient, especially in a long-term perspective. And lastly, but more importantly, life cycle structural engineering should really become the standard in actual engineering practice. So I'm at the very end of my presentation. So much has been done during those years, but there is really so much to do in the future. In the small context of my research, I will try to do some parametric studies to further develop proper value ranges for the classification, and I will surely explore the possibility of including other decision-making parameters in the tool I developed, for example, indoor comfort, but these are only some out of the several possibilities to develop this work. But for now, that's it. Thank you for your attention. I will be pleased to answer to all of your questions.
Thank you very much, Martina. We'll start with the questions by the committee with Professor Marini.
First of all, thank you very much for your presentation. I had the pleasure to read your thesis, and I already congratulated with you because it was really nicely written, very clear, and I do think you provided a quite interesting and relevant contribution for the life cycle structural engineering to be useful and to be used in the future by design professionals. The first thing I would like to ask you is about your classification. You're aware that other authors have proposed different kind of classifications. They would sum up environmental impacts together with life cycle costs by translating environmental impacts into costs. And I would like you to discuss a little bit more your choice to keep these parameters separated.
Okay. Thank you for your comments and for your question. Starting from the classification system, to my knowledge, there are not other classification schemes where in an explicit manner costs and emissions are considered separately. However, other classification schemes, of course, do exist, and they try to consider both seismic and energy aspects, like the one proposed by Michele. And for the other question, which was about keeping separate costs and carbon emissions, because some researchers are proposing to translate carbon emissions into costs, and I felt instead it was more significant to keep them separated, to get more in touch with carbon emissions, to the quantification of carbon emissions, and because I think it is not completely true to do this kind of translation, in the sense that I agree that carbon taxes may be relevant, but in a process like the decision-making phase, I believe they should be taken separately.
Okay, thank you. And then I had another question. I saw you compared different kind of interventions and came up with your radar schemes, which were really clear. I do think that you didn't mention the performance you achieved with all those interventions. And I think it would be more fair to compare ISO performance solutions. What would you say about that?
Yes, I totally agree with you, because actually to be comparable, all retrofitting solutions should be expected to reach the same targets. However, in the framework of my thesis, I just designed each solution to try to apply the framework and see if it was applicable and easy to handle. But in future, I will surely take into account this comment, because necessarily to be comparable, solutions should achieve the same target, especially in terms of carbon emissions, for example. Somehow, to have a really significant estimation of carbon emissions due to the retrofitting intervention only, they really should be similar in the objectives to be comparable in the quantification. I hope I answered.
Yes, thank you. And a final comment. How far are we from the day in which life cycle structural engineering will be used by design professionals? There's a huge work done behind your presentation, and
I hope
it requires also a quite broad knowledge, right? So what do we need for life cycle structural engineering?
I hope we are not so far, because I think it's really something necessary to do in the very next years. And I think that projects like the Lewis one or other European projects may be really useful for that, because they can, the main outputs of such projects may be very useful for practitioners, and they will allow them to really use a practical tool to apply this kind of approach to common practice. So I hope we are near, at least.
Thank you very much.
Thank you.
Thank you. Other questions from the committee? From the audience instead? Michele? You're an habitué.
Yeah, I have a question. Thank you for your nice and clear presentation. And you mentioned invasiveness of the retrofit interventions, which is really something relevant, especially when you intervene on existing buildings. So my question is, have you considered of including that as a specific parameter in your approach?
Not still, but I really think it's something important, especially related to, for example, in residential building, to occupants inside the building. So invasiveness really plays an important role when deciding the optimal retrofitting solution for a building. So I have still not included, but I think I will surely consider in future developments. Thank you a lot.
Okay. Michele now.
Martina, thank you for the presentation. I have a question this time, in the sense that I am afraid I've missed one small point, because in most of the presentation you were referring to per year variables. So, whatever, losses, costs, and so on. But in two slides, and particularly at the end, you were talking about life cycle. Between these two, there is a variable, which is time. And as you know, I don't believe at all in a life duration of the building or a coefficient of importance or these sort of things that are just something invented by someone who wanted to solve another problem with some apparently rational variable which is not rational in my mind. So can you explain a little bit more to me, how did you insert the variable time? What is the life cycle? Over which cycle? How many years and why? And depending on the use of the building or the relevance of the building, the life cycle of a hospital is different from the life cycle of a residential building. So this has not been clear to me, so if you can elaborate, I'll be grateful.
Okay, thank you for your question. I will try to go quickly to the slide where life cycle performance metric were defined. No, okay. I've been too fast, so I'm studying again, sorry. Because in the equation you will see clearly. Okay, here. What I define as a life cycle performance metric is a metric in economic or environmental terms that I wanted to evaluate through the post-retrofit building life. However, since I agree with you that it's not easy to determine for how much years the building will, to consider, how many years to consider after the retrofitting option, I decided to normalize this parameter by the extended life of the building, which of course would need an estimation at the very beginning. For example, for my applications, I considered 30 years for the residential building. However, this may not be necessarily the exact extended life. Maybe it's something that should be discussed with the stakeholders. But in the context of these parameters, I decided to normalize by this number. So I'm expecting somehow this time estimates to be covered in this normalization. When I talk about life cycle, I mean that I'm dealing with the operational, I'm considering the operational phase of the building from the retrofitting up to its end of life. In the sense that for retrofitting, for example, for the end of life phase, I'm only considering the demolition of retrofitting materials only. Because when we plan a retrofitting option for a building, we need to consider the life cycle of retrofitting materials also and account not only for their production in economic or environmental terms, but also for their need of maintenance during their operational time and the costs and carbon emissions associated to their end of life, which hopefully will not only consist in demolition, but maybe reuse or recycle in further applications. I hope I more or less...
It's a convention.
Yes. No, not relevantly. The only thing that changes is the cost of retrofitting options and demolition of retrofitting materials that are one-off costs. So they are not considered in an extended life.
I'm not talking about the same building. I'm saying that there are more buildings and you change the operational duration, the variation of the parameters in different buildings could be different.
Yeah, I think it would change, but I also think that this is related to it's a choice of stakeholders maybe. Okay, thank you. Okay.
Any final question? Okay, I would have one, if you don't. Oh no, there's someone? Oh, sorry, I didn't see the hand raised. Yes.
So thank you very much for this very interesting presentation. I'm Anastasios Chiavos from ETH Zurich. One question I have is that in many of these cases, what is decisive for the owners of the building is to see when they get their investment back, basically the payback period of the investment. While for this more general life cycle engineering approach, you show that much more parameters are important, and basically there is a gap between the interest of the community as a whole and the interest of the owners of the building as to if they will implement these retrofitting measures. And based on this very nice concept that you showed, how do you propose to cover this gap between the interests of the communities and the interests of the owners, which in many cases are more short-term, so interesting when to get the investment back? So thank you very much.
Thank you for your comments and for your question. Of course, the payback period is probably out of the four the most easy to understand for the building owner. That's why it is included in the decision-making process. Because I felt it was not enough just to consider life cycle costs, but it was necessary to also include this parameter. Concerning of course, the owner interest, I think this kind of approaches may be useful because maybe the owner is more interested in the payback period, whilst the designer may be interested in the reduction of more than one parameter. So somehow the owner can decide based on the payback period only, but the designer can suggest other optimal solution where more than one parameter is minimized. Thank you again.
Okay, we can see it's a very hot topic. Yes, I had a question myself because you know I've been interested in this topic as well. Simple one. When you showed different combinations of structural and energy efficiency retrofitting measures, I don't remember you talking a little bit about the criteria that were behind those choices, how you combined them, the choices that you made. I don't know if you want to mention something about that, and how would you go if you would have to actually come up with a proposal for the best combination, for instance? Okay,
yes. For the combinations, I was at the first interested in seeing and checking whether structural interventions only can have an effect in the energy performance of the buildings. So the main reasons for the first choice of the integrated solution for the school building, for example, were dictated from this observation. So I was interested to see whether, for example, joint strengthening with FRP layers, for example, could somehow help in the reduction of thermal bridges. So that's how I started then thinking about the solutions. But after I mainly observed the characteristics of the building. For example, for the energy efficiency upgrade for the school building, it was easier for me to design a thermal insulation of the vertical envelope, whilst the second one, which was characterized by very large balconies, it was impossible to think about it. So since we had a hair gap between the two brick layers in the walls, we decided to introduce cellulose fibers inside this gap.
Okay. Yes.
Something like this.
Yes, thank you. Very clear, very clear. Okay, thank you, Martina, once again.
Thank you.